Hello, everyone. My name is Jack Rummel, and this is the fifth project for the material science. And for my part of the project, we're going to be talking about parts one and two. So, for my part, we had to explain to like a 7 year old in a simple and friendly way, an easy way to understand the difference between an insulator, a semiconductor, and a conductor. So, in order for them to be able to visualize this, I would relate electricity to water. So we're going to think of electricity like water trying to move through different things. So in our case, we have that a conductor is like a metal pipe and that water moves easily through it. And that's how electricity moves through metals like copper or gold, which is very easily. An insulator is kind of like a big rock where water can't move through it at all. And that's how materials like plastic or rubber behave, which electricity cannot pass through them. A semiconductor is in between those two. It's kind of like soil. Sometimes water can move through it, and other times it can't. Materials like silicone, used in phones and computers, they also act like a conductor or an insulator, depending on how we treat them, how we want them to be used. And so, um, in short, summarize a conductor, electricity moves easily. In an insulator, electricity does not move. And in a semiconductor, it acts like both, depending on the conditions. So for the second part, I had to explain to like a first year mechanical engineering student that has some background knowledge the following. So for primary bonds, um, we know that they're the strongest bonds in solids, which is ionic bonds, which where the electrons are transferred between atoms, like table salt. Covalent bond, where atoms share electrons, like silicon and diamond. And the metallic bonds, where they share a sea of electrons that move freely, which is why metals conduct electricity. Basically, I related it to like a sea of electrons, which means they're in water and they can go basically wherever they want, and they're very rapid and they're allowed to move freely. For secondary weaker attractions, we have the van der Waals forces, which is weak attractions between molecules, which is important in gases and soft materials. Hydrogen bonds stronger than van der Waals, and it occurs when hydrogen bonds to oxygen or nitrogen, which is important in water and DNA. And the energy band and band gap theory, it just means that in solids, electrons sit in bands of allowed energy, and conductors, bands overlap, electrons move easily, it means it's a good conductor. Insulators, large band gap, electrons cannot jump, which means there's no conduction. Semiconductor, small band gap, electrons can jump with heat or doping, and this theory explains why metals conduct well and why semiconductors can be controlled, and this is due to the fact that electrons can jump depending on what we want them to do. And then lastly, for my last part of the project, I had to explain why the resistance is equal to rho times the length over the area is a true formula. So for our lab, we measured the potentiometer and we used it. We measured the total length to be 27 centimeters, and the resistance at that length was 40 amps. When we put the length of the potentiometer at 13.5 centimeters, the resistance read 20 amps. And this makes sense because it just shows that doubling the length is doubling the resistance and vice versa. And this is exactly what the formula predicts, because in this case, we know that rho is a constant and the area doesn't change. So the resistance and the length should be a linear similarity between the two, which is exactly what the formula predicts. So this just proves that the formula is in fact true.
Hello everyone, my name is Dimitri, and for my part of the project, I'll be explaining some basic semiconductor concepts and why different LED materials give off different colors of light to a general arts slash literature majored college student. So, what is a semiconductor? A semiconductor is a material that sometimes conducts electricity and sometimes doesn't. It's basically in between a metal, which conducts very well, and an insulator, which doesn't conduct at all. Examples of these are like silicon and germanium. When a semiconductor gets a little energy, like heat, some of the electrons break loose from the atoms and start moving. These moving electrons are called conduction electrons. And when an electron leaves its place, it leaves behind an empty spot. And that empty spot acts like a positive charge. And we just call that empty spot a hole. So electricity in semiconductors is basically electrons moving one way and holes moving the other way. Intrinsic versus extrinsic. There are two major types of semiconductors. First is intrinsic, which just means pure silicon or pure germanium with nothing added. It is in an intrinsic material, electrons and holes naturally appear in equal amounts. The second type is extrinsic, which just means we intentionally add impurities to change how it conducts. So if we add atoms that give extra electrons, it becomes N-type. If we add atoms that creates more holes, it becomes P-type. So this is just how engineers control the behavior of electronic devices. Mobility. Mobility simply means how easily electrons or holes can move through the material. So materials like germanium have higher mobility, so charges are able to move more easily. Silicon has a lower mobility, but it's more stable, which is why it's used in most everyday electronics. So how do LEDs make light? To explain LED color, we only need one simple idea. So when an electron drops into a hole, it releases a tiny packet of energy, and that packet ends up becoming light. The amount of energy released determines the color. So if a big energy release gives off a higher energy colors like green or blue, and a small energy release gives off lower energy colors like red or infrared. So what is GAP versus GaAs LEDs? In pure GaP LED, which is gallium phosphide, the energy drop is big enough to create green light. So pure GaP glows green. But in a pure GaAs LED, which is gallium arsenide, the energy drop is much smaller. So the energy isn't enough to make visible light, so it ends up coming out as infrared, which we can't see with our human eyes. So this is why different semiconductors materials naturally produce different colors. To quickly summarize, electrons and holes move to conduct electricity. Then pure semiconductors generate equal amounts of both. Doped semiconductors let us create extra electrons or extra holes. Mobility tells us how easily charges move. And finally, the color of an LED is determined by how much energy is released when an electron falls into a hole. So GaP releases enough energy for green, and GaAs releases much less, giving infrared. Thank you for listening. And for the final part of this project, I'll be explaining the electrical properties of intrinsic and doped silicon. Then we'll also look at carrier mobilities, intrinsic concentration, conductivity, and then calculate the resistance of a silicon resistor at 300K and at 700K. And then we'll just repeat the same steps for heavily boron doped silicon. So first, intrinsic silicon at 300 Kelvin. The mobility of electrons is about 1350 square centimeters per volt second, and the mobility of holes is about 480. So because the silicon is intrinsic, it has equal numbers of electrons and holes. The intrinsic carrier concentration is about 1 times 10 to the 10 per cubic centimeter. So we just plug this into the conductivity equation. Sigma equals Q times N times the sum of the mobilities. And after substituting the values, the electrical conductivity of intrinsic silicon comes out to about 2.3 times 10 to the minus 6 Siemens per centimeter. So this is extremely low, which means intrinsic silicon behaves almost like an insulator at room temperature. Now let's use that conductivity to find resistance. So the resistor is 1 millimeter wide, 1 millimeter thick, and 1 centimeter long. That gives us a cross-sectional area of about 0.01 square centimeters. So the resistivity is just 1 over conductivity, which for intrinsic silicon is about 4.3 times 10 to the 5 ohm centimeters. And when we just plug that into the R equals rho times the length divided by the area, the resistance ends up being about 4.3 times 10 to the 7 ohms. So if we heat intrinsic silicon to 700K, the intrinsic carrier concentration increases exponentially. That means the conductivity increases dramatically, and then the resistance drops by several orders of magnitude. Now let's take a look at the boron doped silicon with a concentration of 2 times 10 to the 19 per cubic centimeter. So this is an extremely heavy p-type doping, so all the whole concentrations P is essentially equal to the doping level. The electron concentration becomes extremely small because it equals the intrinsic concentration squared divided by the whole concentration. At this doping level, the whole mobility drops significantly from 480 all the way down to 50 due to impurity scattering. When we calculate conductivity using sigma equals Q times P times mobility, we get about 1.6 S per cm. This is many orders of magnitude higher than an intrinsic silicon. And finally, let's just calculate the resistance of the same exact resistor using the doped silicon. So as before, the resistivity is 1 over conductivity, which gives about 0.625 ohm centimeters. Using the same R equals rho L over A formula, we get a resistance of about 62.5 ohms. Compared to the 43 million ohms for intrinsic silicon that we got before, this is dramatically lower, which is why doping is essential for making silicon usable in electronic devices. So at 700 Kelvin, because this silicon is very heavily doped, the number of carriers is dominated by the dopant, not temperature. So the resistance still decreases slightly with temperature, but nowhere near as dramatically as intrinsic silicon. And that concludes the comparison between intrinsic and doped silicon.